Hey ladies and gentlemen, welcome back to a new video. Wow, how exciting. A new unit, a different unit, describing the topics of equilibrium. We'll begin this study and finish a month and a half from now, so we'll spend quite a few weeks engrossing ourselves in this idea of equilibrium and what all an equilibrium constant means. But I wanted to point out real briefly here just a few examples of equilibria situations we've already seen. So in this first example, we take an Erlenmeyer flask, put about half full of water or whatever, and leave it set open to the dry Utah air. Here I said we took out all the gas. Maybe I should have said we took out all the water vapor. But you could trade it. You could evacuate much of the volume space above the water of all gas, or most importantly, just water vapor. You put the lid on and let it set for a while. If the lid's on, that prevents anything from escaping, and what we see is quite a number of water molecules in liquid phase evaporating into the gaseous phase. Quite a few. I don't have a number. Depends on how warm the water is. Also depends on the air pressure a little bit. But in any case, we draw an arrow, one-way arrow describing pretty much, for the most part, the liquid is evaporating into the gas phase. But after this volume space above the liquid becomes more and more heavily concentrated or approaching saturated with water vapor, then some of the water vapor does indeed interact with the surface of the liquid water and the walls of the container and begin to recondense. So some of the gas phase water will go backwards, see that little arrow there, backwards, and create some liquid water. And after a matter of only an hour or two at the most, we would see that we have an equilibrium balance where some liquid water is evaporating into the gas phase, but some gaseous gas phase H2O is recondensing into the liquid phase, not only at the surface of the liquid down here, but also on the walls of the container, maybe even the inside of the little stopper there. So even though it looks like it's just sitting there, we've done some measurements that show that there really are molecules of water changing phase in seeming random nature, but it has to do with statistics and the likeliness of the particles always moving, bouncing into each other. Some of them escape into the gas phase, some of them come back into liquid phase. And we use that double arrow to say that even though it looks like nothing's happening, there's some kind of equilibrium set up between these two, and I would see, if I could see on a molecular level, some evaporation and some condensation, but equal in amount, interestingly, when I reach an equilibrium. Here in the middle, we haven't quite reached the equilibrium yet. We're on the way, but an equilibrium is some process where the forwards and the backwards reaction in chemistry of forwards and backwards events become equal in rates. So after a while, my evaporation rate would equal my condensation rate. I just made this number up, 37 million per second. Could be, quite possibly, depends on how hot or how cold or how big of a sample you have, but there's some number of water molecules going from the liquid to the gas phase, but then there's also that same number of gas phase molecules going into the liquid phase or recondensing into the liquid phase. And that's totally a made up number, but I'm sure I could imagine or do a calculation to describe a situation where that would be pretty close. So even though it looks like it's just sitting there, is there anything happening? And the answer is, yeah, something's happening. In the beginning of this, if we were to graph the condensation and evaporation, looks like the evaporation rate stays just about constant. Perhaps I might even call it zero order, not dependent on how much I have. As long as I have some liquid water there, it'll evaporate the same in the beginning and in the end of our time analysis. But the condensation starts at zero when there's no gas phase water, to increasing quickly at first, and then slowly decreasing to the same rate as the evaporation. So here at this point in time, whatever time that is, I've reached the place where the evaporation and condensation are equal. I'm in a dynamic equilibrium, some kind of balanced state of evaporating and condensing. But even though it looks like the concentrations don't change from that point on, I know something's still happening on a molecular level. Not actually on a macroscopic level, if I were to look at it on a gross level, on a large level, it would seem like after equilibrium has been established, I have the same amount of liquid and the same amount of gas over hours and hours and hours and days and months. But really, if we look at it on a particular level, we still see evaporation and condensation. Another example or bit of evidence of equilibrium is you take some water that's saturated with, say, an iodide ion or potassium iodide. And then, so that, by the way, that means, do you remember, that water cannot dissolve any more potassium iodide. It's holding as much as it can. Then you take some special potassium iodide solid and you dump it to the bottom of this saturated potassium iodide solution. Well, if this is saturated with potassium iodide, then you put more potassium iodide in it, it can't dissolve. No more will fit in the water. But this potassium iodide has a special label to it. We'll make it a radioactively labeled iodide, and that's quite easy to do, actually. After a while, we find out that some radioactive iodide ions do indeed make it up into the aqueous phase, and so some of them do dissolve, being surrounded or solvated or into the water. And so what does that say? That says even if this water is saturated with iodide, that it could still have some particles of potassium and iodide ion coming together to undissolve themselves to precipitate, while we still have some potassium iodide in the solid state dissolving back into solution. So I would say, I don't know, maybe 23 million per second units per second dissolve and 23 million units per second undissolve, and that radioactively labeled iodine is a way for us to track or trace on a particulate scale, an ionic scale, or on a molecular scale, that there are really collisions still happening and dissolutions happening and recrystallizations happening. Here's another cool little picture I saw. Just trying to show the same story of, even though it looks like perhaps, even though it looks like perhaps I have solid salt, NaCl, sitting on the bottom of a beaker, and it's just sitting there, there really is something happening on the particulate level. There will still be dissolving and there will still be recrystallizing, but it looks like once I do reach equilibrium on the macroscopic scale, like the concentrations of this and this and this aren't changing. One more example. I take a piston and cylinder, and it looks like I have propane. Propane. Liquid propane. It actually wouldn't be a liquid unless I compressed it a little bit, but you can do it pretty easily. And so here's liquid propane down here, and a few gaseous propane molecules, 5 cartoon molecules up here, and a whole bunch of cartoon molecules down here. And if I put the lid on, just leave it set for a while, it'll reach an equilibrium state where I have a certain number of propane molecules in the liquid phase per second moving up into the gas phase, but that doesn't happen alone. I see the reverse arrow is the reverse process is also occurring, where I have propane gas molecules colliding with each other and the liquid sample down below, and actually recondensing at the same rate as the evaporation happens. What did I mention? I forgot what I said. The same number. Turn around and go back the other way. So I have an equilibrium situation of, just like with water, this doesn't matter what the sample is. But then I maybe change the equilibrium a little bit. Let me change the situation. I raise this plunger up a little bit higher, so I allow more airspace, more volume up here. Well, what will that do to the equilibrium? The answer is, as we'll see in the later part of this chapter, it's called Le Chatelier's principle. It'll throw the equilibrium off. The balanced mixture is confused. Or in other words, if I have more space up here, does it make sense that I will somehow allow more of these liquid phase molecules to evaporate up into the airspace? So now instead of 5 cartoon molecules, I have 1, 2, 3, 4, 5, 6, 7 cartoon molecules, just trying to say that I will have more particles escaping up into the gas phase than I had over here. But that doesn't last too long, because eventually if I left this piston here at the increased volume, then this would increase for a while, but as it increased to a certain point, then the gas phase to liquid phase would increase. So this arrow would eventually grow equal to this arrow in size, if you want to use the size of the arrow as some kind of representation of how many per second are going in which direction, as is sometimes done. Conversely, if I squeeze this piston to a smaller space, they've shown only 3 cartoon molecules in the gas phase. In a sense, that squeezes those gas phase molecules back into the liquid phase. That's not exactly proper, but it's a macroscopic, simple-minded approach to say that the rate of condensation from the gas phase to liquid phase increases, decreasing the evaporation as the pressure would, be built up above it. But that wouldn't stay like it either if you just held this piston right here with this new fixed volume, yet decreased. The condensation would increase initially, but as soon as it condensed, as soon as more and more, how should I say this? We would reach a new equilibrium after a relatively short period of time, where I would still be able to find, although these 2 arrows would end up probably being smaller than these 2 arrows. Ooh, that's a tough question. I'll have to reassess that statement, but in any case, if I let it sit here, it would reach some kind of new equilibrium or new balance state that would be different than the initial balance state. But Mother Nature loves there to be an equilibrium. If I personify her, I do it all the time. She loves there somehow to be an equilibrium, a balanced mixture between one state and another. And it's not always black and white. It's always some kind of coming and going, forwards and backwards. I better shut up before I get myself in more trouble. I'll see you in class. Thanks for watching, guys.